I'd like to have a discussion about what the mass moment of inertia really means and in some practical ways. I've titled this little sub-lecture, K trumps R. And sometimes shapes are ideal, and we've seen some things that are pretty close to ideal, like a bowling ball here. Oops, sorry. Bowling ball is pretty much a uniform sphere. Maybe a pulley might be close to being a uniform disc or a uniform hoop, but most of the time things are not ideal. And we're going to get a lot of shapes that look something like this, where there's some mass distributed out there. Maybe we got something with a hole hogged out of the middle of it, a tire or a spool. They're clearly not ideal. They're some sort of a composite of maybe several shapes. Maybe it's integrated. Maybe that's how we got there. But in general, the mass moment of inertia is often pre-computed in these cases in the form of a radius of gyration. And so we'll use K instead of R to find CG. So on any problem where K is given to you, use that instead of R. But we're going to talk about why. All right. Let's talk about what the mass moment of inertia really means. All right, so I, we've talked about, is resistance to rotation. And we know that our equation is moment equals I alpha, so the bigger the I, the smaller the alpha for any given torque or moment that's driving it. One of the uniform shapes is a disk where the mass is evenly distributed. We know that the formula there for mass moment inertia is 1/2 mr squared. An extreme would be if instead of having it evenly distributed, that the mass is all focused out on the edge. And we know that to be a ring or a hoop, and we're going to call that mass moment of inertia mr squared. Another extreme, maybe not as common, but to try to focus the mass in the middle. How does that work? Well, it's probably not going to be ideal, or probably not going to be a reality where you have a shape that's out here that actually doesn't have any mass and all the mass is focused in the middle. But we might have some shape that is kind of close to that, where it's really, really heavy in the middle and really, really not very massive on the outside. But if we did have a point mass, what that says though, if we did have all the mass pointed in the middle, that would say that the radius there was equal to 0, and it would say that there was no resistance to rotation. So everything's focused in the middle, and if you put a torque on there, that would offer Ig would be equal to 0. So what we're saying here is Ig of a point mass is equal to 0. I about G of a point mass is equal to 0. Okay, and this is can also be seen by looking at the parallel axis. So if you have a point mass out here, again we say that the mass moment of inertia about its own center of gravity is equal to 0. But if you're located about some other point with some lever arm here, then it's not equal to 0. And we'll use the parallel axis theorem to understand that. But I about O is equal to I about G, which is 0, plus md squared. So we know that IO for a particle, a point mass as a particle, was equal to md squared. The same thing is happening if you have a collection of point masses on a ring here, and we may want to put some torque on there. We'll have the sum of the mr squareds. We may have a spoked wheel, and where basically all the mass is focused out there, and that'll be mr squared. These people here on this teeter-totter can be modeled as point masses, so that you can see that it will have a mass moment of inertia about A, the fulcrum, which is m d squared, and this will be m d squared, so that there is still some mass moment of inertia about the middle, even though the mass moment of inertia of itself about its own center of gravity is equal to 0. So I about A is equal to md squared, and you could have a sum of those. All right, let's look at this bar. A bar has its mass evenly distributed, and we know that the mass moment of inertia is 1/12 ml squared. What if that same mass was concentrated at the ends? In other words, we put all of the mass out at L over 2 on each side. We have m over 2 and m over 2 separated by L over 2. We can find out the mass moment of inertia about the point, about G, the center of gravity of this whole thing now, is equal to the sum of md squareds, which is 2 times m over 2. We've got two masses, m over 2, and the d is L over 2 squared, and we can see that the mass moment of inertia of that about about a barbell, if you want to call it that, about the center is 1/4 ml squared. So we have made the mass moment of inertia 3 times larger by, instead of distributing the weight evenly, we shoved all the weight out there in the middle. So what does this mean? In general, if you push the weight out, you make the mass moment of inertia larger. We know that to be the ring, the same with a ring. We've seen that with now a bar. A disc is the same thing. So what we know then is that the way to increase the mass moment of inertia is we give it more mass with the same radius. That helps us. We give it more radius with the same mass, or we can shove everything out to the edge and give it the same mass, the same radius, but distribute the mass all out at the edge. That can, in many ways, we can increase the mass moment of inertia if we want to. Okay, let's look at fixed axis rotation. Again, there's some things we can discover here that more than one shape can have the same mass moment of inertia. The mass moment of inertia is just a number, and it can be computed by a variety of different ways. But let's say that this is a round thing that has a mass of 1/3 of a kilogram. It's got a radius of gyration of 0.1, an r of that. So all we have to do is find out what our mass moment of inertia is by mk squared. We can find out it is 0.0333. We can have a bar with a 1 kilogram mass and a length of that, 1/12 ml squared, and we get 2 shapes, completely different masses, and they have the same thing. So what that means is under a torque, under a moment, they will behave exactly the same. Since that moment is I alpha, or the alpha is determined by the I and the moment, they'll have the same angular acceleration given that same moment, even though they're completely different. Okay, so again, the shape basically doesn't matter. As long as it has the same mass moment of inertia, it will behave the same. All right, now here we have a hoop versus a disc. We know that the hoop has greater mass moment of inertia because the weight is concentrated out on the edge. Same with the disc, or versus a disc. Same thing with the barbell. If the weight's concentrated out there, it's going to be greater than a bar. And so we've seen that moving the mass out to the outside increases the mass moment of inertia. How far out can you go? What's the greatest mass moment of inertia you can achieve then by shoving the weight out there? Well, the question is can you push it out farther than the radius? Is there a shape with a mass moment of inertia greater than mr squared? Mr squared is shoving it out to the edge. The answer is no. The mass moment of inertia maximum is going to be mr squared. You can't push the weight out farther than the radius. In other words, that's the farthest out you can go. And since we know that I is equal to mk squared, k max, the mass moment or the radius of gyration, cannot be greater than r. And so what we're going to see now is k is going to be a number between 0 and r. It can't be any bigger than r. All right, there we go. It can't be a number. It will be a number between 0 and r. All right. All right. Just another look. The radius of gyration takes the mass out of the mass moment of inertia. Different shapes can have the same k value. We've kind of just already talked about that, and you can see my examples here. Different shapes, different, let's see, do we have, I think I don't really compute the mass here. All I'm doing is just suggesting that they have different k values. All right. And a shape can be made from different materials with different mass to vary the mass moment of inertia. In other words, you can have one shape that looks like this with spokes in it, and you can make it out of different masses, different materials, so that can vary the mass moment of inertia. You can make it out of aluminum, or you make it out of steel, or maybe out of wood, or something like that, all having the same k, but they'll have different mass moment of inertia with different material. So k then is the distance from the center that the mass would be concentrated at if you could concentrate it there. So in other words, if you could push all the mass from evenly distributed and concentrated at a point or 2 points like this, then k is the distance from the center that the mass would be concentrated. I don't know if that makes any sense, but it was kind of a revelation a little bit to me is what that really means is that's the distance from the center if all the mass could be concentrated there. And we can find out the K from a variety, find out the K value of a variety of common shapes. Here we have a ring, and it has we know that it's mr squared. We've already talked about K is equal to R for a ring. Well, what's the K value for a disk? Well, 1/2 mr squared is equal to mk squared. And we can compute K is equal to 0.707, or a ball of 0.632. Again, you can see that we already discovered that K has to be a number between 0 and R, and so there's a fraction here. It's not greater than R, clearly. It's less than R, and it's going to be a fraction that is something between 0 and R. A rod, if you put all the mass out at the edge, it would be 0.577, and I'm putting R here as L over 2 because that makes more sense for a rod. Let's see, do I have anything else? Okay, so bottom line here is that the only way to describe the mass moment of inertia of most shapes is using the radius of gyration. You can't really use an ideal shape most of the time. You use the K value because that's the appropriate way of describing a complex shape. Okay, sometimes K is discovered empirically. So here's a problem out of the book where we're looking at some things, but let's just change the problem around a little bit and let's try to discover the K value by saying that the mass is going to be released from rest. The speed at the bottom when it gets down here is going to be 3 meters per second. Let's find out what the K is. So I'm going to use energy to discover this, and I'm just going to say T1 plus V1 plus U naught is equal to T2 plus T2. I have my beginning energy is 0. I have some mgh that it's starting with. There's no friction, and so there's no work, and at the end it's going to have no potential energy, but it will have some kinetic energy. And we discovered this in class, where the kinetic energy of a composite shape is going to be a combination of 1/2 mv squared of the weight plus the 1/2 I omega squared of the round thing, and just add those up, and I can see that the K value of this shape, giving this performance, in other words, I'm going to release it from rest. I'm going to say that it's going to go 3 meters per second. Trying to find the K value of that is just plugging it into there, and I can say that K is equal to 0.194 in meters. All right, so sometimes we'll compute it based on an experiment. Sometimes we can find it by looking at the geometry. So here, let's find the K value of this composite shape. In this case, this is the whole minus the holes. You use this a little bit in statics, looking at the area moment of inertia, and sometimes using trying to find centroids using the whole minus the holes. And so what we're going to do here is use the whole minus the hole concept to find out what the radius of gyration is and the area moment, mass moment of inertia. So in this problem, we're going to try to find the IG, the radius of gyration, and I about O, which is right up there. So we're going to call this piece of material, we're going to call it plywood, and we're going to say that it weighs or has a density of 500 kilograms per meter cube. It's going to be about 25.025 meters thick, 1 inches thick. And we know that, and this probably makes the most sense to us, I think, in the whole minus the whole, so the whole here minus the whole. We're going to say that the net mass is going to be the entire thing minus what we take out, so the whole minus the whole. The mass is going to be the area times the thickness times the density. So I'm going to say the whole mass, if this whole wasn't there, would be 1.4 squared times the thickness times the density is 24 kilograms. The whole itself is the same density, so it's going to be the area times the thickness times the density is going to be 6.2. So the net mass is going to be the whole minus the whole, which is 18.217 kilograms. Okay. We use the same kind of thing to try to come up with mass moment of inertia. We're going to do the whole minus the whole there. All right. So in this case, we're going to say the whole, looking in the back of the book of a rectangular shape, the mass moment of inertia about the middle, about right there, is going to be 1/12 m, and not 1/12 ml squared, but 1/12 m times a squared plus b squared, where the a and b are the sides. And then I'm going to take out the whole, this whole, and we're going to assume that it is the same uniform density as if it's a whole W if it's a round thing, it's going to be modeled as a disk. So that would be where the mass is uniformly distributed. That's what a disk is it's uniformly distributed. So I'll take out that 1/2 mr squared of the whole. All right, so 1/12 ml squared of the outside plus minus 1/2 mr squared of the HOLE, and I get the IG of equal to 7.5. All right, how can I find the radius of gyration then? We know that that is equal to, I is equal to mk squared, so k is equal to the square root of I over m. I have the I about g, I just computed that. The mass, I computed right up there. So we're going to use the net mass here because that's what I've got, and I can find that the radius of gyration is 0.6146 or 0.6416. And then to find out the mass moment of inertia about another point, I'm going to go from here. I'm going to go from I'm going to go from this point and go up to here. I'm going to use Ig plus md squared using the parallel axis theorem. So that's what I got down here. IO is equal to Ig plus md squared, and you can see that that is obviously greater than here. Remember when we use the parallel axis theorem, move it to a point outside of the center of gravity, it always makes the mass moment of inertia go up. It never makes it go lower. And we can see that I about O is that.